So last time we looked at autonomous differential equations, which are these first-order differential equations where the right-hand side only depends on x, and there's no explicit t dependence. And we saw that there's a way to analyze these equations without actually solving them. Even though, in principle, you could solve them because they're separable. So if you can handle the integral, you always end up with this kind of situation with autonomous differential equations. So if you can handle this integral, then that's great, you can solve. But often that is not an easy integral, and it's just great to know that you can still figure out what's going on without actually solving. So we used some techniques on examples, but I want to just sort of bring everything together so it's somewhat automated. So let's just, I guess, let's put the phase line down here. So this horizontal line here is the phase line. And then let's plot x prime against x. So this will be basically the function f of x. The outputs of the function f of x will be on the vertical axis. So something maybe like this. Actually, let's do this. How about that? How about this? So I can show you all the things that can possibly happen. Okay, so here's a plot of what f of x might look like. And we noticed that for the phase plane, for the phase diagram, phase line analysis, it matters where the critical points are. Those are the zeros of f, so the values of x that make f 0. So after you, let me put this in yellow like I was doing before. After you solve the equation fx equals 0, and you get some solutions, possibly more than one solution, then you call those x star. Then these solutions, these are called critical points. So in this picture, they would be these points where the function f, which I'm plotting here, takes the value 0. So this picture shows you 3 critical points. Then all of these are equilibria for the system. So this starting differential equation has an equilibrium at each of these yellow points. Meaning, if your initial condition, if at time 0 you start at one of these yellow points, then you will stay there forever. In other words, x of t equals that yellow dot, that value of x there, is a solution, a constant solution to the differential equation. However, we saw that you can have stable equilibria and unstable equilibria. So an equilibrium is stable when changing x away from that yellow dot tends to make x just go right back to the yellow dot, to just go back towards it. And an equilibrium is unstable when changing x away from the yellow dot makes it actually run away from the yellow dot even further. So in this picture, between these two equilibria, between these three, some are stable and some are not stable. So let's look at this one. What if, let's think about this region here. If x is in this region, if the state of your system is in this region, then what happens to it from there? Well, x prime is then positive, right? So it would just increase. So if it's in this region, then x would increase. If x is in this region, then x prime would be negative, so x would decrease. If x is in this region, x prime would be positive, so x would increase, and in this region it would increase. And you could always focus on how quickly it increases or decreases if you want to. So for example, I could put in some more fine-grained information and be like, okay, well, as you get closer to this yellow dot here, you increase more slowly. Maybe I can depict that by making a tiny arrow. And as you get closer over here, you increase more slowly. And over here, you increase slowly. Over here, you decrease slowly. Here, you increase slowly. I'm saying slowly because I'm looking at the magnitude of x prime. Like here, the magnitude of x prime is pretty low, right? But here, it's higher. That's telling you how fast the increase or decrease is. So here, the magnitude of x prime is pretty small. But it's positive, so it's increase. All right, so there's how we would get the phase diagram out of the plot of f of x. But I want to show you a way to get the phase diagram without having to plot f of x if you want to. If you want to not plot f of x, there's something you can do. So now we can definitely point out which equilibrium is stable. This one is stable, right? Because if you move away from it, then if you change x so that it's away from the equilibrium, then x will just tend to go right back to the equilibrium. This one is unstable. And this one, okay, this is a little interesting. So this is clearly a sort of extra special case, right? Because it's a 0 of f, but it's not a situation where f is passing through 0. It's a situation where f is just barely touching 0 and then going back and becoming positive again. So something different is going on here. And you can see if you change x by decreasing it a little bit from this yellow dot, then it will increase back towards the yellow dot, which is stable type behavior. But if you increase x away from the yellow dot to the right, then it'll run off to the right. Yeah, and my head gestures are actually flipped around compared to what you should see. So this is my right. Oh, that's interesting. Maybe I should flip the camera feed at some point. Okay, well, anyway. So what do we call this, stable or unstable? So to come up with a name, we need sort of a more clear definition of what is a stable equilibrium. Okay, so here I'm starting to write out a more precise definition of what is a stable equilibrium. So a stable equilibrium, x star, will be a state for which, so meaning a value of x, for which any small change to x away from x star leads to the state x approaching x star. So approaching x star means as time goes forward. So sort of in the long term, as t goes to infinity, as you let time run forward, this changed x slightly away from x star would go back and approach x star. So that's a stable equilibrium. And an unstable equilibrium is just anything else, a not stable equilibrium. Okay, so an unstable equilibrium is an equilibrium that is not stable. Okay, now with this precise definition, we can say exactly what's going on with this yellow point here. Is it stable or not stable? Well, for it to be stable, it would have to be the case that when the state is this much, this yellow value here, then any small change away from that point leads to the state approaching that point again as time goes on. So is this stable? Is it true that any small change I make away from this, be it to the right or to the left, I will have my state approaching back to this point, trying to return to this point? No, that's not true, right? It's not true that for any small change, I will have my state attempting to return back to this point. Because if I move to the right, then the state, my x runs off to the right, runs away. So this is unstable, because it is not stable, according to the definition of stable. Okay, so this picture kind of shows you the various things that can happen, but do you need to actually plot f every time? No, you can get all of this information and build the phase diagram pretty much without plotting f if you focus on the derivative of f. Okay, so that's a little bit confusing. We should be clear. What do I mean by the derivative of f? I don't mean this kind of derivative. So here, what you see is dx dt, right? On the left side here is the derivative with respect to time, dx dt. When I say the derivative of f, I mean the slope of this plot here, which is not going to be df dt. So there is such a thing as df dt, but that's not what I'm talking about. I'm talking about the derivative of f with respect to x. This will tell you, derivative of f with respect to x will tell you the slopes on this plot, which is an f versus x plot, right? So if you look at the derivative of f with respect to x and then you evaluate that at the various critical points. So take this and look at it, look at its value at each critical point, at each yellow dot. Then seeing if it's positive or negative will tell you whether you have this kind of picture, where it's stable, this kind of picture, where it's unstable, or this kind of picture. Here the derivative of f would vanish, right? The slope of the white plot here is 0, where it's also unstable. So that's it. That's how you can get all the information for the phase line that you need by just focusing on the function f and doing some calculations without making any plots. Just look at the derivative of f. If the derivative of f is negative, so let me make a new picture that's on its own. So let's suppose, say you have x star equals f, sorry, not x star, x prime equals fx. And this is your differential equation, autonomous differential equation. Then say you found a critical point. X star. Meaning you just found that f of x star equals 0. That's all that means. Then on your phase line, so maybe you will find many critical points, but let me just focus on one. So on your phase line, somewhere there's this yellow point, x star, right? And you want to know, is it this kind of picture? Is it this kind of picture? How does x behave when you start out with initial conditions not at the critical point, but near to it? So this is a question that I claim you can answer by just looking at the derivative of f with respect to x. So take this and evaluate it at x equals x star. If you get something positive, then that means when you make that plot of f versus x, it looks like that, right? Positive slope, which means that to the left of the yellow dot, you would, if x started out with an initial condition to the left of the yellow dot, then you would observe decreasing x. And if x started out to the right, then you would observe increasing x. So this is an unstable equilibrium. On the other hand, if this were less than 0, then you would expect this for the portion of the plot of f of x versus x that passes through this yellow dot. Then to the left, you would expect increasing behavior, and to the right, decreasing behavior. That's a stable equilibrium. So that's information you can get by just computing the derivative and evaluating and looking, is it positive or negative? No plots needed.